There are various theories in the motion of the planets, and there are different people with different ideas from their time periods. Each philosopher attempted to expand on the thoughts of past philosophers. One of the earliest philosophers was a man named Copernicus, who invented the Copernicus system. This was the first modern European theory of planetary motion that was heliocentric. An example that placed the sun motionless at the center of the solar system with all the planets, including the Earth, revolving around it. Copernicus developed this theory in the early 16th century from a study of ancient astronomical records. He retained the ancient belief that the planets move in perfect circles, and therefore, like Ptolemy, he was forced to utilize epicycle to explain deviations from uniform motion. Copernicus laid the foundation for all the astronomers and were the primary person to begin the research of the universe. From Copernicus' information, another science searched into the planets. This person was named Johannes Kepler, and he was a Platonist, which meant that he looked for mathematical laws of planetary motion. Kepler came up with 3 laws of planetary motion, and they are stated as: the first law of Kepler's indicates that all planets move about the sun in an elliptical orbit with the sun at one focus. In an elliptical orbit, the distance between the planets and the sun varies. The appearance of an ellipse looks like a square circle. It has one long axis called major axis. Perpendicular to major axis is minor or shorter axis. Foci is defined as 2 points symmetrically located on major axis either side of center ellipse. An ellipse is a lot of points for which the sum of their distance from the foci is a constant.
According to Kepler's first law, the sun is a focus and it gives off a large force, but the velocity remains tangential to the ellipse. The sun's mass compared to that of the planet is immense because it is about 99.86% of the total in the solar system. Thus, its gravitational attraction is sufficient to continually accelerate the bodies of the solar system towards itself. The second law, a line joining a planet to the sun sweeps south in equal areas in equal intervals of time. The third law, harmonic law, states that the squares of the period of revolution of the planets about the sun are in the same ratio as the cubes of their mean radii of their orbits. The equation for this law would be quantity Ta over Tb raised to 2 equals quantity R over Rb raised to 3. Another equation for the harmonic law is P equals Ka raised to 3 over 2, where P equals a sidereal period and A semi-major axis. For example, if A is measured in astronomical units and side real periods in years, then the constant K in mathematical expression for Kepler's third law is equal to 1, and the mathematical relation becomes P squared equals A cubed.
It's found by using the equation above. AU equals the semi-major axis of Earth's orbit. Kepler became an assistant to Tycho Brahe, who made accurate observation of the planets in the year 1600. After Brahe had passed away, Kepler continued his work. By calculating planetary orbits to a percentage accuracy, Tycho Brahe was a Danish astronomer who developed a systematic approach for observing the planets and stars. He stressed the importance of making such observations on a regular basis. Brahe's observation of planetary motion revealed that the tables then in use to predict the positions of the planets were inaccurate. His sightings of supernova, type of exploding star, in 1572 helped disprove that the theory that no change could occur in the heavens beyond the orbits of the moon.
Sir Isaac Newton hoped on the same path laid out by Copernicus, Brahe, and Kepler. He discovered the law giving the centrifugal force on a body moving uniformly in a circular path. Centrifugal force is an apparent outward force experienced by a rotating body. It is fictitious in the sense that it is not part of an interaction but is due to the tendency of a moving body to follow a straight line path. Newton's idea was to image the Earth's gravity influence the moon because the moon's centrifugal force wants to continue in a straight path, but the Earth has more mass and force which causes the moon to rotate. This counterbalances the centrifugal force from this law of centrifugal force and Kepler's third law of planetary motion. Newton deduced the inverse square law.
In order to support Newton's inverse square law of gravitation, he used the orbit of a comet which appeared on November 14, 1680 as an example. This particular comet remained visible until December 5, 1680, when it began moving closer to the Sun where it could be observed. When it appeared weeks later, it was traveling away from the Sun in the same path where it first approached. Newton united various concepts and mathematical laws of motion in one uniform theory with gravity as the cause of planetary motion. He agreed with Kepler on his second law that the force acting on a planet must be directed towards the Sun. This means that the acceleration of the planets is directed inward to the Sun because it serves as a focus according to Kepler. Also, the speed of planets are an elliptical orbit, so the velocity is tangential like a circle. Newton's law of gravitation states that objects in the universe attract each other with a force that varies directly as the product of their masses and inversely as the square of the distances from each other. The theory of universal gravitation deals with the force of gravity, which is one of the fundamental forces in nature. Every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This force acts along the lines joining the two particles. That gravitational between any two masses in the universe can be found by the equation F is equals to G times quantity m sub 1 times m sub 2 over D squared.
In the equation above, m1 and m2 are the masses of the two particles. R is the distance between them, and G is a universal constant, which must be measured experimentally and has the same numerical value for all objects. In 798, Henry Cavendish confirmed the law of universal gravitation and determined G as well. The accepted value of G is equals to 6.27 times 10 raised to negative 11 newtons times m squared over kilogram squared. This is a very important law because it describes why objects fall to the ground when dropped and also why planets orbit the Sun and the Moon orbits the Earth. In conclusion, we found that all the research and information we gathered for planetary motion is totally accurate. Kepler's second law is correctly stated based from our references too. Newton's law of gravitation is a reliable source of information. This will help you understand a little of planetary motion, why planets move around the Sun, and what else can explain to us the movement of planets.
Then bend my knees every time the beat drop. Hey, this CIP, man, can't go to South. Rock, then bend my knees every time the beat drop.